Well, I'd like to welcome all of you on this beautiful hot summer day to what will be the best part of your day, I'm sure. Thesis defense from Sam Chevalier. He's going to talk about using real-time statistical data to improve voltage stability in stochastic power systems. Sam came to us from CBU, Union High School, and did his undergraduate in electrical engineering here at the University of Vermont, and as hopefully, depending on how he does today, will finish his master's degree here and then is off to a PhD program at MIT with a good friend of mine, Osio Teresa. And so this is work that he's done some pretty interesting stuff. So I'm really looking forward to this, and I'd like us all to welcome Sam.
Well, thank you all very much for coming here today. It's an honor to have you all here. I'd like to extend a special thank you to my track coach, Greg Wisser, who was my coach for the last 4 years for being here. Joe Gavin, he runs Chi Alpha here at UVM. Very glad that you're here too. Also to my committee members, Dr. Omasaki and Dr. Lukova, and also Dr. Hines, who has been my graduate advisor this last year. So of course they say the key, or the most important point to preparing an effective presentation is to know your audience when you're preparing your material. And my audience ranges from Dr. Hines, who is one of the premier experts on dynamic modeling of cascading power system failures, to my cousin Kelly McClintock, who recently asked me if I study the dangerous or the safe type of electricity, to which I answered yes, thank you. So without further ado, using real-time statistical data to improve voltage stability in stochastic power systems. Here we go. So I'd like to demystify the title by just picking apart the different components. So first, using real-time statistical data. So this depends on leveraging these little blue dots, which are scattered throughout the transmission system, and they're known as phasor measurement units. And they are capable of taking very high sample rate measurements of voltage and current throughout the transmission system, anywhere from 30 to 60 hertz, and relaying this information back to control centers in real time for grid operators to make decisions about stability and control of the power system. And this is a map from 1.5 years ago. And every month, more and more of these units are being rolled out. And someday in the future, we're going to have pretty much full observability of the transmission system based on things I've read. So we're working on research that can start to really leverage this data and make real-time stability assessment determinations. And so in order to, the next portion of the title is improving voltage stability. So I just want to read a brief excerpt of a paper entitled Voltage Collapse in Complex Systems, which says the term voltage stability has been appropriated over decades of research to refer to many different static or dynamic stability concepts ranging orders of magnitude and timescales. We make use of the long-term quasi-static notion of voltage stability, which corresponds to the way the high voltage solution of a power network should change under small load perturbations during regular operation. This is the notion of stability most relevant for guarding against static voltage instability collapse. So I read that because if we were a room of power systems engineers and you tasked us with defining voltage stability and assessing it in a power system, the room might turn into a brawl by the end of the conversation because it can be a contentious topic, as Dr. Hines and I have learned. So we will be employing the definition of voltage stability that says a power system's ability to uphold steady voltage magnitudes at all network buses after experiencing a disturbance. And the methods and the control action that we're going to be considering today will fall under the category of long-term voltage stability because we're going to be managing reactive power resources and active power resources. So an example of a system which lost voltage stability occurred back in 1987 on an unusually hot day in Tokyo, Japan, when thousands of air conditioning units were turned online very rapidly after a lunch break. And around 1:10 p.m., the system experienced what's known as a saddle node bifurcation, and voltages began to fall around the system very rapidly until there was a series of line trips that led to a cascading blackout, and around 1:15 p.m., there was a large blackout. About 3 million customers in TEPCO's service area lost electrical power. So this is an example of pretty severe voltage collapse, and it's something that we hope to help avoid with some of the stability metrics that we're introducing today. So the final part of the title, to demystify, is the idea of a stochastic power system. Now, a stochastic process is one in which we can use a random variable to describe the probability distribution function of the process, and its value at any given time might be unknown or it's random, and we don't know it until we measure it. So what we do with power systems is we develop these power system models. So here's an example of the IEEE 39 bus system, and as is pretty standard with transmission analysis, we've assumed we're dealing with a balanced three-phase system. So we convert the system into a single line diagram so we can apply what's called per phase analysis in order to simplify the mathematics. And this model, I'll explain the stochastic nature of it in a moment. You'll notice that the transmission infrastructure in the New England model for some reason doesn't include the Vermont transmission infrastructure, which Bernie Sanders was pretty outraged about. That's actually why he ran for president, because he wanted to put Vermont back on the map. Of course. So when we're dealing with these systems, we're dealing with these differential algebraic equation models, which are shown in compact form in equation 1, which contain differential and algebraic variables, system parameters, lambda, and control settings. And what we've done in our analysis, instead of using one single variable for the system parameters, lambda, we've separated it into two variables, s and u, where s are the slowly varying system parameters, and u are the quickly varying system parameters. And to get a more intuitive sense for these things, here's an example of some differential variables in the swing equation. We have our control settings, which are governed by p, and then we have our algebraic variables, y, and here are our system parameters, which control the load in our system. And again, to get a more intuitive sense for what S and U mean, here's a load curve plot from Velco, which is the Vermont Electric Power Company. And the blue curve shows the aggregate load for Tuesday, April 13th in the state of Vermont. And the red curve shows the aggregate load in New England, courtesy of ISO New England. In Vermont, we call this the champ curve because it kind of looks like champ due to the distributed solar and its effects on the grid. Anyways, what I've done to that plot is I've applied a Gaussian kernel smoother, and I'm using S to model the slowly varying load throughout the day. And I've peeled off the noise, and I'm modeling that with U of t, which is the quickly varying load. And I plot these signals on top of each other, and they look something like this. And when we do our voltage collapse analysis in our analysis, we're mainly looking at the algebraic power flow equations. But when we run our time domain simulations, we want to consider the dynamic stability and the rotor angle stability of the system. So we need to incorporate both of these noise models in order to fully gauge the stability of the system. So quickly I'll outline how we model these two parameters. S, which is the slowly varying parameter, we model it with a Gaussian probability density function where we have a diffusion coefficient and a variable t for a given time period. And also for the quickly varying quickly varying load parameter, we govern it with an Ornstein-Uhlenbeck process, which is Markovian, mean reverting, and you can see that the quickly varying process is zero mean, and also that this process is uncorrelated with itself in time and with other loads around the system, according to our noise model. So as we think about the idea of a bifurcation, we have to understand bifurcation theory in order to gauge the stability of a power system. So a bifurcation is when a system undergoes some sort of a critical transition and divides into multiple branches. So this occurs in a power system when a parameter, such as load level, increases until it encounters a bifurcation, and so some sort of instability might ensue. And because of the quantitative change in the solution space of the mathematical models that we're using for the power system model, simply decreasing that load level back to its original value may not restore stability once the system has experienced a bifurcation. So there are a range of colorful spectrum of different types of bifurcations that a system can experience. We're most concerned with the saddle node bifurcation, where when we have a system of equations, we have an unstable solution and a stable solution, and as a parameter increases, these two solutions coalesce and eventually disappear once the parameter increases by too much. We also have the idea of a Hopf bifurcation, which we gauge by considering the dynamics of the state matrix, A sub s, and we track the eigenvalues of that matrix. And when the real part of one of the eigenvalues of the state matrix crosses into the open right half plane, we'll have a dynamic oscillatory instability. And again, we're more concerned with the saddle node bifurcation, but but it's important to consider both types of bifurcations, because oftentimes the Hopf bifurcation will occur before the saddle node bifurcation, where the saddle node represents the maximum power transfer point of the entire system. It's typically when the saddle node bifurcation will occur. So in order to get kind of a deeper sense for the saddle node bifurcation, we think about the traditional power system structure, where we have generation, transmission, distribution, and consumption. And we have this kind of flow of energy. And to gain more of an intuitive concept for how the energy might flow through a system like that, I'm going to draw an analogy to a sport that you only hear about if either it's an Olympic year or if you're at my thesis defense, which is pole vaulting, where we think about Sergei Bubka, who's one of the greatest athletes of all time, where his goal is essentially to transfer the kinetic energy of his approach run into elastic potential energy of the bending pole, and then into useful gravitational potential energy. And ultimately, the transmission and distribution systems are highly analogous to the bending of the pole. And any system which is used as a conduit for energy transfer can at some point experience what we call the maximum power transfer point. So here we see Lazaro Borges from Cuba. This is 4 years ago yesterday at the London 2012 Olympics. He's jumping for 5:35 here, loads the pole, and extends. And that pole experience was known as the maximum power transfer point, and it experienced a type of bifurcation. We'll see it again in slow motion. Start to get a sense for the severity of the bifurcation. The pole has snapped, and there's no going back. So we would like to avoid that sort of event in a power system. So in order to get a more quantitative sense of how a saddle node bifurcation might occur in a power system, we consider one of the most advanced power systems of all time, the two-bus system, where we have a generator bus on the front bus, we place a small load on the two-bus, and we have small line mittens. We add to that shunt losses, a tap-changing transformer, and variable shunt support. We apply the nonlinear AC power flow equations at the load bus. We square them, we sum them together, we write Q in terms of a power factor parameter beta, and then we're able to solve for the magnitude of the two-bus voltage analytically. And once we have that expression, we can draw what we call nose curves, where as load increases, we see that the voltage at the two-bus decreases until a point, which is indicated by the little orange dots that I've drawn, until a point where the system reaches what we can think of as static voltage collapse, or the saddle node bifurcation. And what you can see from these plots is that as we increase shunt support, the system can handle more and more load. But what you'll also notice is that as we increase shunt support, the point of maximum power transfer is increasing, or is rising, and it's getting closer and closer to some nominal system voltage, where this is 0.9 per unit. So as another example, I plot another nose curve here, where again we show the standard nose curve, and in this case, as load increases, I continuously increase the shunt support to regulate the voltage high. So the voltage magnitude stays high, but what I've plotted in the blue trace is the squared derivative of the nose curve. So even though voltage magnitude is staying high in this trace, we're seeing that the squared derivative is still increasing. And why that's important to consider is that because when we have an analytical expression for the two-bus voltage magnitude, we use the delta method, and we take the square of the derivative of the nose curve, multiply it by the load noise, and that gives us bus voltage variance. Now, bus voltage variance is something that we can measure with these phasor measurement units, and so we can use it as an early warning sign. I apply a little bit of more analysis, and I'm plotting the bus voltage variance here on the y-axis, and I show that as system load increases, bus voltage variance starts increasing without bound. So you can see how it can be a rather useful early warning sign for pinpointing instability in a power system. So we categorize this phenomena as critical slowing down, which is an event that's been seen in ecosystems, climate models, power systems, any sort of nonlinear system that is tending toward instability can experience critical slowing down. And it's primarily indicated by statistical increases of variance and autocorrelation among state variable time series measurements. And these statistical increases are primarily due to two reasons. Here we see a stable system with a deep basin of attraction. Here we see an unstable system with a more flat basin of attraction. Number one, small perturbations push the system farther from the equilibrium point. And number two, the system takes longer to recover from small perturbations. So as a power system is approaching a bifurcation, these two phenomena start manifesting themselves. So work that my predecessor, Dr. Ganavati, has done is he's quantified these increases on a variety of different power systems, or I guess mainly the 39 bus power system. And so here we see the bifurcation point, and here we plot bus voltage variance and bus voltage autocorrelation, and you see they increase dramatically as we approach the point of bifurcation. And these can be very useful signals for grid operators. Here we see grid operators stationed at Belco, the Vermont Electric Power Company. What's important to understand, though, is that bus voltage variance is most closely tied with the saddle node bifurcation and reaching the point of maximum power transfer, where the Hopf bifurcation is more tied, or the autocorrelation, the voltages and currents, is more closely tied to the Hopf bifurcation and destabilizing generator dynamics. In the projects that I've been working on, I'm more concerned with the saddle node bifurcation, and that's what I've been working to mitigate primarily. I haven't been considering the dynamics so much. So several months ago, Dr. Hines and I wrote a paper entitled Identifying System-Wide Early Warning Signs of Instability in Stochastic Power Systems, SPS. And the basis of that paper, which I'll share just very briefly, pretty much we developed we build the power flow Jacobian, and we set the delta P sensitivity equal to 0. Then we perform a basic cron reduction. I'm just going to blow through this very quickly. We perform linear algebra on this reduced power flow Jacobian, develop these participation factors, and we're able to show that the participation factors corresponding to the smallest eigenvalue of the Jacobian matrix very nicely pinpoints which buses in a system are going to be showing the highest bus voltage variance. So these are our time domain simulations. This is what fell out of the linear algebra, and this is an analytical method that other people from our research group have developed, which I'll review in several moments. And so right now we've moved on to writing another transactions paper entitled Using PMU Statistics to Reduce the Probability of Voltage Collapse. And I'll overview the objectives of this paper. So the first objective of this new paper is to use bus voltage variance to determine when control action in a power system needs to be taken. And the second objective is to show that bus voltage variance is a more useful measure when assessing the stability of the system than simply using bus voltage magnitude for reasons that I've shown on the two-bus system. Third goal of this, or objective of this paper is to explore how these control actions can signal active and reactive power injection to restabilize the system. And finally, number 4, we wanted to test this algorithm on both a small system, the 39-bus system, and a larger system, the Polish network, which I'll introduce soon. So in order to accomplish these 4 tasks, we had to build several tools, or leverage different tools from the literature. One of them comes from work that Dr. Ganavati again did with Dr. Hines and Dr. Lakova. And the goal of this tool is to derive the algebraic covariance matrix of the system using our system model and given our stochastic inputs. So we start with our system, we linearize using the Taylor series expansion. We perform a substitution to eliminate the algebraic variable sensitivities, and then we come up with z dot equals az plus b psi, where that equation is governing the dynamics of the system. And we can solve the Lyapunov equation numerically in MATLAB to build sigma squared sub z, which is the state variable covariance matrix. And then we simply apply linear transformation on both sides of the state variable covariance matrix to build the algebraic variable covariance matrix. And a subset of the diagonal entries of sigma squared sub y are equal to the analytical bus voltage variances. And those are very useful for us as we make control decisions. The second tool that we've decided to leverage is the holomorphic embedded load flow method, or HELM. And the idea behind HELM is instead of solving power flow using traditional iterative techniques such as Newton-Raphsa, we develop a holomorphic function, E of S, at each bus in the system. And that holomorphic expression can be expressed as an infinite power series, as shown here. And then HELM has been around for this technique has been around for several years now, and the process for solving power flow with HELM is pretty well documented in the literature. It consists of solving for these unknown power series coefficients using a recursive technique and the germ solution. And then using a Pade approximate to approximate the power series expressions. Finally, we use standard AC power flow equations to solve for the power injections at each bus in the system. This is very useful, and Helm has all sorts of cool attributes, which I won't get into here. But what we're more interested in is using Helm to solve the continuation power flow problem, where essentially we want to be tracing the nose curve in a large system. And typical methods use Newton-Raphsa to iteratively keep solving the system as load is increased. We're able to use Helm a little bit differently, though. So an idea is presented in a master's thesis that came out of ASU last year, and pretty much it allows us to scale the holomorphic parameter lowercase s, and in doing so, increase the loads at all of the buses, and then analytically compute the bus voltage phasors. There's some drawbacks with the method that's presented because it doesn't allow for alternative loading rates in the continuation power flow problem, and it only allows for one generator bus in the system. So I did some work on their method and improved it slightly by taking the power balance equation for a PQ bus and inserting k sub I, which is a loading rate parameter, which if k sub I is set to 0, then the loads don't change as s is scaled. If k sub I is set to 1 or -1, then loads are going to scale appropriately. Also, we make an assumption about the voltages at the PV and the reference buses, or the generator buses. And so when we have a system operating under a certain paradigm, we solve the base case power flow solution, and then what we do with that base case power flow solution is we fix the voltage magnitude and the voltage phase angle at all of the PV and the reference buses. And so then as we scale load at the PQ buses, these voltages stay fixed. And pretty much generation is increased at the generators proportional to the electrical distance that the generator is from the load increase. So that's kind of assumption we've made to make the mathematics work a little bit more simply. The details are spelled out in my thesis document, and I work hard to justify this assumption. I'm just going to give a very quick taste of the algebra that is used to solve Helm, or to solve CPF using Helm. So we start by using this power balance equation at the PQ bus and embedding it with a holomorphic parameter S. Next, we expand the power series explicitly, and we generalize this expression to solve for the nth power series coefficient, because the n equals 0, or the germ solution is already known, assuming that we've solved the base case power flow solution. So we separate this into the real and imaginary components, and then we do just some basic linear algebra to solve for the nth power series coefficients. Once we have the nth, we can solve for the n+1 using a recursive technique, n+2, n+3, for as many iterations or